Hey everybody, welcome back to another AP Precalculus video. So today we're going to be going over 1.9 rational functions and vertical asymptotes.
Here are our learning objectives, and we're going to figure out where vertical asymptotes are in rational functions and the end behavior at vertical asymptotes.
So just a refresher on what a rational function is a function consisting of the ratio of two polynomials. So it's essentially one polynomial divided by another polynomial. So you can see that x squared plus 3x minus 12 is a polynomial, and it's over 5 plus x to the third, which is another polynomial. So s of x and m of x are polynomials.
So there are going to be some domain restrictions when dividing polynomials. Obviously, when m of x in this scenario is equal to 0, this will make the function y undefined. And the input values that make m of x 0 are going to be values where there's a location of a whole or a vertical asymptote in the graph. Okay, guys, so now we're going to be talking about vertical asymptotes. And a vertical asymptote occurs when a factor in the denominator cannot cancel out with a factor in the numerator. So in this equation, f of x, we see that there's an x minus 6 on the top and the bottom. However, if we cancel an x minus 6 from the top and the bottom, that results in there being 1x minus 6 at the bottom. Since all the factors didn't cancel out, that tells us that there's a vertical asymptote at x equals 6. Okay, so now we're going to move on to two examples. You guys can pause and try these if you would like. All right, guys, so this is the first example we had. And to approach this question, first, you should factor the numerator and the denominator. And when you do that, you should get x minus 3 times x minus 8 over 2 times x minus 4. So we can see that there's no common factors in the numerator and the denominator. However, that's fine because there's a factor in the denominator that does not cancel out with a factor in the numerator, and that's x minus 4. So that tells us that there's a vertical asymptote at x equals 4. All right, guys, so this is the next example, and this one's already all factored out. So if we cancel the x minus 3 in the numerator and the denominator, we're left with an additional x minus 3 in the numerator, and that's not the definition of a vertical asymptote. So in this example, there's no vertical asymptote. However, there is something known as a whole at x equals 3, which you will learn about in the next lesson.
All right, so next we're going to be talking about limit notation and vertical asymptotes. So we have worked with limit notation before, but now we're going to specifically use limit notation to express the behaviors of a graph as it approaches a vertical asymptote. So this is how you write a limit statement. You have limit, and then you have your function name, so f of x, and then you have x approaching a. So a is going to be the input value being approached. So in this case, if we're talking about a vertical asymptote, a is going to be the value of a vertical asymptote. So if your vertical asymptote, for example, is at x equals 5, your a is going to be a 5. And if you have a plus at the top right corner, that means you're approaching that vertical asymptote from the right. And then if you have a minus, you're approaching that vertical asymptote from the left. And I'm going to have a picture on the next slide so you can see what I mean by that. And then this part is either going to be a negative infinity or a positive infinity. So negative infinity means that the graph is going downwards as you're going towards that vertical asymptote. And then positive infinity is the graph is going upwards as you're going towards the vertical asymptote. The way you would read this is as x approaches 5 from the right, f of x increases without bound. Our vertical asymptote is going to be at x equals 5, so you can see that there's a vertical asymptote right here. Since there's a plus at the top right corner, we're approaching the vertical asymptote from the right side. So here we have the right side, and you can see that as we're going towards the vertical asymptote from the right side, the graph goes upwards, hence the infinity sign right here. So this is just what this translates to on a graph. So now we're going to figure out how to write the left and right limit statements for a rational function as it approaches its vertical asymptote. So here are the 6 steps that we're going to be going through, and here's the example we're going to be using to go through these 6 steps. So the first step is to factor out both the numerator and the denominator. So if we're given this rational function right here, we want to factor them out. For the AP exam and for most tests, if this is a non-calculator portion, your factors aren't going to be like huge numbers like they are here for the most part. So don't worry too much about that. We just gave harder examples so that you can see that it applies for like larger numbers as well. When you factor these two polynomials out, you get x plus 7 times x minus 16 over x plus 7 times x minus 9. The second step is to cancel out common factors between the numerator and the denominator. So x plus 7 is present in both the numerator and the denominator. You're going to cancel those out. All right, so step 3 is find the zeros of the remaining factors in the denominator to find the vertical asymptotes. So the last factor in the denominator is going to be x minus 9. So our vertical asymptote is going to be at x equals 9, because if you plug that in, that just makes the denominator 0. So now that we know that where our vertical asymptote is at x equals 9, we're going to plug in input values to the left and right of this vertical asymptote into the canceled out equation. So you don't want to include the x plus 7 when you're plugging in your values. So we're just going to be left with whatever's remaining. And then an input to the left of x equals 9 could be 8.9. And then an input to the right of x equals 9 could be 9.1. So we're going to plug those into our canceled out equation. And you don't necessarily have to know like the number values. You just want to know if your outcome is positive or negative. So 8.9 minus 16 is going to be negative, and the 8.9 minus 9 is going to be negative. So overall, f of 8.9 is going to be positive. And then again, 9.1 minus 16 is going to be negative, and then 9.1 minus 9 is going to be positive. So you're going to have a negative outcome for f of 9.1. So when you have a negative outcome, that means that the graph goes downwards. So the graph is going to be approaching negative infinity. And if you have a positive outcome, the graph is going to be approaching infinity. Since f of 8.9, which is on the left of our vertical asymptote, is positive, so that just means that when you're approaching x equals 9 from the left, your f of x graph goes upwards. And then since 9.1 is to the right of your vertical asymptote and it's negative, then that just means as f of x approaches your vertical asymptote from the right, we're going to go downwards. We're going to go towards negative infinity. And then we're just going to take all this information and put it into limit notation. So if we break it down, we have our vertical asymptote is x equals 9, so x is going to be approaching 9. And then from the left side, we're going to go upwards, and then from the right side, we're going to go downwards, so you got the negative infinity. And that's how you write your limit notation. And then just to show that on a graph, it's a little bit harder to see, but you can see that we have our vertical asymptote x equals 9. And then from the left, so from over here, we're going upwards, just as we calculated. If we're approaching the vertical asymptote from the right, we're going downwards. All right, so here's an example that you can pause and do yourself. So it says, write a left and right limit statement for f of x as it approaches its vertical asymptote. We're just going to be following the same steps as earlier. First of all, you want to factor your equation. So we factor it out and we get x minus 5 times x plus 17 over x minus 2 times x plus 17. So since x plus 17 is on both the top and bottom, we're going to cancel this out. And then we're left with x minus 5 over x minus 2. If you plug 2 in for x, that would make the denominator 0. So that's going to be our vertical asymptote. A vertical asymptote at x equals 2. And then values to the left and right of this vertical asymptote, we're going to plug into this canceled out equation. So you have 2.1 to the right and then 1.9 to the left. So when you calculate it, you're going to get a negative for 2.1 and then a positive value for 1.9. So since, again, 2.1 is to the right, so as x approaches our vertical asymptote from the right, we got a negative outcome. So we're going to go downwards, so negative infinity. For 1.9, since you're to the left of that vertical asymptote, you're going to have the negative here, and then we're going upwards, so increasing without bound. And this is decreasing without bound.
All right, now moving on to the final questions. Here we're going to practice an AP style question, and it's telling us that there's a function that has a 0 at x equals 5 and a vertical asymptote at x equals negative 2. I'm just going to go through each answer choice and explain if they are right or wrong. Okay, first we need to see which functions have a 0 x equals 5. We can see that option A doesn't. It has a 0 x equals negative 5. Option B doesn't either, as we can see that there's no factor of x minus 5 in the numerator. Now option C and D both have x minus 5 in the numerator. However, since there's an x minus 5 in the denominator of D, we can eliminate D, which tells us it's C. Also, we know that there's a vertical asymptote at x equals negative 2, since in the denominator, there's a factor x plus 2 that doesn't cancel out with the factors in the numerator, leaving us with 1 in the denominator. So there's going to be a vertical asymptote there. So the answer will be C. For the final question, we are told that the graph of a rational function g has a vertical asymptote at x equals 3. So we need to look for the function that shows that there's a factor of x minus 3 remaining in the denominator after they all cancel. We can immediately eliminate a, and b looks right except it's x plus 3. And for there to be a vertical asymptote x equals 3, it has to be x minus 3 as the factor. So we can cancel a and b. And then for c, since x minus 3 cancels out with the denominator, we know that that is not going to be a vertical asymptote, which leaves us with option D. And we can see that after we cancel the factors, there's going to be 1 remaining in the denominator. So that's why our answer is D.
Thank you guys so much for watching 1.9 Rational Functions and Vertical Asymptotes.
Stay tuned for more AP Precalculus and SAT math videos. Bye!